Okay, so welcome back. We'll move on to next chapter, which is about adding forces. So where does this fit in, right? So far, you've learned what is force, right? So far you've learned what is a force. And then we've learned that there's different types of force. Okay, types of forces. And we have learned free body diagrams, which is a way to find out all the forces on a body, on an object. Okay, so we've learned how to find all forces on an object, right? And that's using free body diagrams, or it's a good way to represent it, right? We've learned how to do it with asking the two key questions. Do you remember what they are? Right? You ask what's touching the object and what's not touching the object. And that's a foolproof way to make sure you don't invent a force that is not there on the object. It's very easy. Students make a mistake to double count forces, as we'll see shortly. And also ask yourself what's not touching it yet will still produce a force. And as far as this quarter is concerned, the only force that plays that role is gravity, right? There is a couple of things more to say before that, but I want to skip ahead a little bit first and immediately see some applications, how this ties in with vectors, to ask the next question of, all right, now that I have found all the forces on an object, right? So we know how to draw free body diagrams from the middle. Even if you're pushing it from the left, you draw. It's basically, the way to think about this is, it sounds a bit counterintuitive, even though I'm touching this surface, but I want to draw it from here. It's because we want to, free body diagrams is you want to put yourself in the situation of this object of interest, right? So you want to, basically you're asking not what forces is applied on it, but what forces does it feel, right? So just to recap, right, a physical diagram would be, all right, you're pushing on it. So you might draw something like this. That's good. That gives you a physical intuition of what's going on. But for free body diagram, we are interested in what the object feels, and it feels being pushed this way. Okay, and we're for most of this course until the very end, we're going to focus on all of the feelings. It's funny that objects are feelings, but all of how it feels, all the impact of the force at the center of mass. Okay, this is an approximation. This is not true. We're approximating basically these things as a single point, and all of its feeling is concentrated at a single point. Turns out this is a very good approximation. It's very effective. We'll deal with extended objects at the very end. Okay, so that's what we have so far. All right, let's say we have all the different types of force, gravity. Let's get rid of the physical diagram. And maybe someone else is pulling it, right? There's a pulling force here. There's a pushing force here. There's gravity going on here. Maybe it's on a table, so there's a normal force from the table. There might be friction from the table as well, so which opposes the motion or the tendency of motion. We'll talk about all that. But the next question, so this starts to get very complicated, right? So how do we add up everything? Another motivation is, if you remember when we talked about the first law and second law of motion, Newton's first law and second law, we have the word net force. Right, net external force, right? Just to clarify that again, external force means, as it obviously means, from outside, because the box itself, it's made out of molecules, right? It's made out of different particles and molecules inside, and there's like intermolecular forces tying them together. Let's not worry about that. Those are all internal forces. I think we don't need to worry about a rigorous definition of what's external force, but basically anything outside of the box pushing, applying on it, that's called external force. But now we need to deal with the term net force, okay? Net force is also known as resultant force or total force. Okay, you might be wondering, well, total force sounds very simple. Why don't we just use that word and need to call it resultant or net force? You'll see it very soon. But today we're going to address the question of how to add forces. Okay. All right. So how do we do that? Now we'll split it into two parts. Split this video into two parts, right? The first part we'll deal with adding forces in one dimension. And just one dimensional motion. And it's incredibly simple, okay? And also, but it's still not naively just adding all the numbers together. So let me give you an example, right? So if I have a box over here and I'm pushing it, right? And someone else is also pushing it. Okay, let's just worry about the horizontal ones first. So by one dimension, that means forces that are either horizontally or purely vertically. Okay, so forces along a line that doesn't go along a plane. So let's say A is pushing it this way and B is pushing it that way. Okay, so what are the free body diagrams, how should I draw it? Let me actually draw it separately to emphasize that free body diagram should really be, everything should be local on a point, right? So if A is pushing it, right, let's draw the physical diagram here, right? So A is pushing it this way, B is pushing it this way. So what does the box feel, right? Free body diagram is about off the box. Right? It's about what the object of interest, I'm interested in the box, not the hands at this point. What does it feel, right? So ask yourself, what does it feel? Well, from A, it feels a force being pushed to the right, and from B, it's feel a force being pushed to the left, like this. Okay, it's slightly counterintuitive because if you think about it, sometimes you might think, oh, this is A is on the left, right? So, but the force is pointing to the right. B is on the right, but the force is pointing to the left. Okay, so just be careful about that. If you ask yourself what the box feels, then that usually resolves all the issues. Okay, so let's say this guy is pushing it with 5 newtons of force, let's say 10 newtons of force. So A is pushing the box with 10 newtons, B is pushing it with 5 newtons. Remember the units for forces, we measure it with newtons. So roughly the force of 10 apples, roughly the force of 5 apples, right? Push it. All right, so what's the total force that, on this object, right? So we have the box like this, being 2 forces being applied. What's the total force acting on it? Is it 15? No. That's not how we define total force, because one of them is pushing this way, the other is pushing it this way. So the total force, we need to add them like vectors. And we need to remember that this 5 newtons is counteracting the other. So it basically renders 5 of these newtons useless. Okay, so the net force is actually PA minus PB instead of PA plus PB. How do I know it's minus? You can see that well, they're opposing each other. Okay, so also remember force is a vector quantity, so it also has a direction. Okay, now we're let's stick with, remember, giving directions is also a non-trivial issue if you do it properly. Give 3 pieces of information, but in one dimension things are easy. You just need to give 1 piece of information, either left, right, plus, minus, up, down, whatever. It's just 1 piece of information. If I say right, there's no ambiguity, right? Yeah, so this is just the magnitude and the direction. Let's put it in brackets. It's to the right. Okay, so to the right, there's 2 ways to think about it, but we'll go with this first. So PA is 10 minus 5. So finally, we have 5 newtons. Okay. And remember to also state the direction. So the magnitude, the net force, is 5 newtons to the right. Okay. Now let's change up the example a little bit. And instead, let's say I'll just draw the free body diagram. PB is 10 newtons and PA is 5 newtons. Okay. What's the net force? In fact, if I do it properly, I should draw a shorter arrow for PA. I don't have to be, well, technically I should do it to scale. That should be exactly half of this, but in an exam and most of the situation, our diagrams, it's just to help us visualize it, and we're not too worried about it. So you don't need to measure it exactly, but it's good to sort of have a rough sense at least, right? If this is larger than this, make this arrow larger than the other. Thinking about it, I probably should shrink this as well, but you get the point. So the net force this time, right, is also, well, which way is the net force going to be? The net force is going to be this way, so it should be left. Okay, and how many units? should I do 10 minus 5 or 5 minus 10? Well, magnitude, here, notice I don't have a vector sign because I'm just calculating the magnitude of this. The direction is taken care of, right? I'm dealing, and this is a general tip, is to separate out the magnitude and the direction calculation separately, all right? So the magnitude is always positive. So take the larger one, subtract the smaller one. Okay, again, 5 newtons, like this, to the left, okay? All right, so very easy, right? So, but let's clarify out what I mentioned. So the general tip is deal with magnitude and direction separately. Okay. So see one more example with 1 dimension, and let's move on to the 2 dimensions because 1 dimension is pretty straightforward. So let's say if I have a car, right, and it's running on the road, and this time we do include friction, one of the rare cases we do. And so at first it has an engine, so it has a driving force from the engine on the car. And let's say there's also a little bit of friction, so a smaller arrow than that one. Usually we use little f to denote friction. So this is from the ground on the car, right? Okay, and let's say we have a driving force of 1,000 newtons and a friction of very small, just 1 newton, like that. Okay, so again, very simple. What's the net force? So deal with the magnitude and direction separately. The magnitude, take the larger one, subtract the small one. Another, if you like, you can put an absolute value, but usually it's simple enough that you can just determine which one subtract which one. All right, so it's 999 newtons. And this is a easy mistake. A lot of students would just leave it like this, right? And write down the magnitude. Remember, no arrows on top means magnitude. Just write that and forget about the direction, right? So when someone asks you a force, remember, always need to specify direction. And since this is a 1-dimensional problem, very easy. Just left, right, up, down, positive, negative, whatever is relevant. Oh, which one should I use? Well, obviously not up, down. You can use left, right. If you want to use plus or minus, then you need to tell me which way is plus and which way is minus. Most of the time we choose the right-hand side to be plus and left-hand side to be minus, just like an XY grid. But you will see later on, it's not necessarily the case. For example, if I have one of almost a famous meme of physics studying boxes on inclined planes, well, which way is plus? Well, maybe this way, but if I have it designed this way, the box is going to fall this way. Is it plus or negative? It's not quite sure. So if you want to use plus and minus, make sure you tell people which way you're defining your plus. So I'm defining this way as positive. For example, you could define this way as positive. And then in this case, the box will be sliding in the positive direction, for example, right? So have in my notes just writing that down as right, but just as an example for you, if I define somewhere this way is my positive direction, then I can say this is in the positive direction. That is also completely fine, okay? Or you can just easily write it as towards the right or something like that, okay? All right, 1 dimension, very simple. That's called net force. And I think now you see why it's also called resultant force, because it's the result of that. And also total force, it's almost like adding them together, but sometimes it's subtract, okay? And so here, maybe I will let you think about this. If I have, let's put 3 forces on it actually. So if someone is pushing it this way with 5 newtons and someone else is pushing it, let's call it P1 and P2. I don't like subscripts that much. I'll put a prime. It makes things more confusing than they need to be with 10 newtons, but there is some friction of 2 newtons. Okay, so the question is, what is the net force? Remember magnitude and direction, right? I'll leave you to this. Okay, we'll talk about forces in 2 dimensions in a second.